Alrighty, hello friends. It is so good to see you all again. Now, today we are going to talk about just a few different things here, as we're going to continue going into polynomials that are a little bit bigger. So yesterday we did quadratics. Today we're going to be looking at polynomials that are of a higher degree. And so I know last year when we were out towards the spring, you guys didn't necessarily get into polynomials a whole heck of a lot. Just because, well, with COVID, we were not here. So higher degree is how we classify level per se of our polynomial or our function in general. So if it's written in general form, this is general form of a polynomial, just like we have general form of a quadratic, we say the largest exponent, well, that would be the degree. So that means that right there, that would be the degree. So say I give you some sort of function like this, y equals x to the 7th minus x cubed plus x squared. And let's make that minus 1. It's in general form. So that means the degree then would be the largest exponent. In this case, the largest exponent would be a 7. So we'd say then that this has a degree of 7. So this is a 7th degree polynomial. Now some polynomials have names, like a 3rd degree polynomial, we call it a cubic. Or a 4th degree polynomial, we call it a quartic. 5th degree is a quintic. But really anything after 5, we just say polynomial of degree n. Polynomial, so this would be a polynomial of degree 7, or you could call it a 7th degree polynomial. Also, we don't just classify polynomials when they're in general form. Sometimes we want to classify them when they're in their factored form. Now, if they're in their factored form, let me throw one up here for you. We calculate the degree a little bit different. So what we do here on these, so we're going to put all our factors here, x plus 4. Let's go x minus 3 squared. And let's try x plus 1 cubed. Oh, I'm kind of running out of room here, aren't I? Doesn't help that that guy, that little pencil right there is. There we go. X plus 1 cubed. All right. Now, if it's in its factored form, the way we figure out the degree is to add up all the degrees or all the exponents of each factor. So if you notice, I have 4 exponents, 4 factors with exponents. Let me see if you can see them here. We've got a 1. If there is no exponent, we assume it's 1. There's a 1 there. There's a 2 there, and there's a 3. So if I add up all those numbers, then I would get the actual degree. In this case, the degree would be, and I'm just going to write D for degree. The degree would be 7. Again, this would be another 7th degree polynomial. It's just where the first one was in general form, the red one is in general form, this purple one is in factored form. Okay? So the first thing you got to be able to do is you got to be able to figure out what is the degree of a polynomial. So let's see here. I'm going to give you guys one. I'm going to give you guys a little bit of a trick one here, just because I feel like it. Well, we'll go x plus 2. And x minus 1 cubed. And let's try x minus 4 squared. All right, go ahead and pause the video real quickly and see if you can determine what the degree is of this polynomial. All right, here we go. So we have no exponent, there was 1. Notice, this term right here, there is no x. So just because there's a number in front, it's not an x, we don't include any exponents there. So there is nothing to include there. We only do exponents of factors. And if we have a single x, that's actually x minus 0. That would be a factor. But a straight number, that's not a factor. We call that a leading coefficient. All right. So if I add up my degree here, if I add up my variables, my exponents, sorry about that, my degree would be 6. This would be a 6th-degree polynomial. So when we're dealing with polynomials, we can either have a degree that is odd or a degree that is even. It can either be odd or it could be even. Now, leading coefficient test. Well, before we talk about the leading coefficient test, chances are we probably need to make sure we all know what a leading coefficient is. So that leading coefficient, that is some number in front of our first term, if it's in general form. So this would be a leading coefficient. Efficient. Always hard to follow the rules there. Let's see here. Whoop. There we go. Let's make that a little bit smaller. And then we'll bring this over here. All right. So our leading coefficient is that number in front. So let's take a look at this factored one here. What do you think the leading coefficient would be? Let's see here. Leading coefficient on this one would be, again, the number in front of the first term, or if it's in factored form, just the number out. That means this would be a leading coefficient of 2. So we'd say then the leading coefficient would be 2. All right, why don't you pause the video here and see if you can figure out what the leading coefficient is on this degree of 6 one we have. That's right. We have a degree of 3. I'm sorry, a leading coefficient of 3. So LC would be 3. Notice, our leading coefficient can be a positive number, and you guys are probably already guessing the leading coefficient can also be a negative number. So our leading coefficient, it could be a positive number. Or our leading coefficient could be a negative number. So we have degrees, we have leading coefficients. Well, what that does now is this leading coefficient thing, it allows us to determine what these graphs, when we start to graph these, it allows us to determine whether these graphs, where they start and where they end. Now, I had a teacher I used to work with over at Wood Creek. Her name was Michelle Zuhal. Fabulous teacher. Fabulous teacher. Now, she had a dance for this. She called it the leading or the end behavior dance. And I'm not going to lie, when I left Wood Creek to go to Whitney, I took that dance with me. I got to give credit where credit's due. Again, if we steal something from somebody else, got to make sure we always give credit. All right. I don't know. Didn't mean to make them go from smaller to greater, but it's all right. So like we saw here, our degrees can be odd and they can be even. So a degree could be odd. There we go. A degree could be odd. or a degree could be even. Our leading coefficient can either be positive or our leading coefficient could be negative. So if our leading coefficient is positive, it's like the slope of a line. If it's positive, it means it's going up. So in other words, if it's positive, that means it's going to, oopsie, that's not good at all. We wanted arrows for this. There we go. If it's positive, it means it's going to end going up. Where if the leading coefficient is negative, it's going to end going down. So again, positive, going up, negative, going down. So we use the leading coefficient to determine if the graph is going to end high or end low. If it's going to end high when it's positive, or if it's going to end low when it's negative. Now, odd and even, odd people always do things differently, right? So if it's odd, same thing with the graph. It's going to be doing something different. So instead of, if it's going to end high, well, odd graphs will do the opposite. So they'll start low. If it's going to end low, it's going to do the opposite. It's going to start high. Even graphs, well, they're going to do the same thing. So if it starts high, it's going to end high. If it's going to start low, then it will end low. So the leading coefficient tells you if the graph opens up or down. The degree, odd, will tell you if it's starting on the same or opposite side. Even will tell you if it's starting on the same or opposite side. Opposite starts on the, or odd functions starts with O. Opposite starts with O. They start opposite each other. Even, they'll start on the same side as where it finishes. So first thing you need to know is, what is that leading coefficient test? We should be able to, some people call it the end behavior test. We should be able to tell if the graph is going to open up or down, or is it going to start low or start high, and is it going to finish low or finish high? That's the end behavior. On top of that, something else that we need to know is what happens to the roots. Now, a root is nothing more. There's a whole bunch of things that mean the same thing. There's X-intercepts. Hyphen, there you go. And I'm going to just give it a random variable. It doesn't matter. I'm just going to call it P. All right. So an X-intercept would be written as a point, where a 0, that's just the actual X value. Same thing with a root. That would just be the X value. Same thing with a solution. All these things mean the exact same thing. It's just where a 0, a root, a solution is written as a X value, an intercept is written as a point. So we have 3 different types of roots that we use most common in our functions. 3 different types. And we classify them based upon the degree of that factor, of what it looks like. Now, here's what a factor looks like. I'm just going to put an X-intercept up here so you guys can see it. And I'm just going to say this X-intercept is the number C. It doesn't matter. If it helps you out, make it a number. It doesn't matter. So I'm going to say this root right here is, well, let's make it 1. Okay, so that's the X. That's a 0, or a root that's 1. By the way, if the root is 1, notice then if I were to write it as a factor, that means I set it equal to 0. this factor would be x minus 1. How do you turn a root into a factor? Just set one side equal to 0. X minus 1 equals 0. X equals 1 is the root. X minus 1 is the factor. All right, so I'm going to have this x minus 1 all the way up here. Now, there's three different types of roots that we're going to look at. The first one is called a root that goes through like a line. It looks a lot like a line. So it's going to come up and it looks like a line. This happens when the exponent is 1 or not there. We call that a single root. The next kind is kind of what we call like the bounce back root. Looks like a parabola. All right, we call that a double root. And the reason why we call it a double root, think of a parabola. X squared gives us a parabola. Therefore, this has an exponent of 2. We call that a double root. And I don't think it's going to, if I say triple root, I think you guys could probably figure out pretty darn quickly what that exponent will be. It would be 3. Now, triple roots form an inflection point. So for those that don't know what an inflection point is, let me show you. It comes up, and it looks really steep, and then it flattens out, and then it goes up again. So it goes steep to flat to steep. Whether that's going up or going down, steep to flat to steep. So we have our factors. And now we can describe the root by its multiplicity. We would say that this is a root of just 1. Okay, we don't need to say that it's a single root. We could. Now, a double root, we're not going to, if we were solving this, we wouldn't write x equals 1 twice. What we'd say is x equals 1, and since it has an exponent, and exponents mean multiply, repeat a multiplication, well, that's the same thing with the root. So we'd say it's multiplicity of 2. That exponent is the same as the multiplicity. So friends, go on out on a limb here. This is x equals 1. What do you think this multiplicity is going to be? That's right. Multiplicity of 3. Cool. All righty. Well, let's just keep right on going here, friends. So we're going to be playing with this idea here just for a little bit. What we're going to do in our notes here, it already had all this stuff here for us, but we're going to try to see where this all came from. We're going to make a sketch of this graph. Okay, a sketch of this graph. Now, first of all, let's see if we can figure out why the things work. It says the degree is 4. Why do you think that is? Well, if it doesn't have any exponents, we make them 1. And if we add up all those exponents, I have 1 plus 1, or plus 2 plus 1. I have 3 exponents, and they add up to 4. So therefore, the degree is 4. Look at my leading coefficient. See if you can figure out what my leading coefficient is going to do. My leading coefficient is a -2. So if my degree is even and my leading coefficient is a negative number, that means my end behavior is both tails down. That's what you call the arrow. We call it a tail. Okay, that means where does it start? Where does it end? They both are facing down. So it looked like this. So I have a tail. Since it's the negative, the leading coefficient being a negative number. That tells me if the graph's going to start high or low. Well, it's going to finish low. Sorry about that. Tells me where it ends, finishes low. And then the degree, I'll use 2. The degree here tells me if it's going to be the same or different. So if the degree is odd, it's going to start opposite. But if the degree is even, like this one does, it's going to be the same. So it's going to start low. Ends low, start low. And by the way, both tails down. Notice how both arrows are pointing down. To find our zeros, we're going to take every factor and set them equal to 0. So we're going to take every factor here and set them equal to 0. So if we're looking for our zeros here, we have x plus 3. So we're going to take each factor, and we're going to set them equal to 0. X plus 3 is 0. That means x is negative 3. So that would be a root. It goes from a factor to a root. Factor to a 0. Root and 0, same thing. Take your next factor, x minus 1. So there's my factor. I set it equal to 0, and I get my root, or my 0, positive 1. Take my next factor, x minus 5. And I solve it to get my root, or my 0, which is a positive 5. Now, friends, once we have our roots, we're going to have to go through real quick and figure out, do any of these have a multiplicity? Well, this had a 1. That doesn't do anything for me. This had a 1. That doesn't do anything for me. But this one right here, the x minus 1, had a 2. Therefore, this has a multiplicity of 2. So if I'm going to go through and I'm going to graph this thing, and we are going to graph it real quick just to kind of take a little look-see at it. And we're going to go ahead and put some dots on here while we graph this. So I had 1 at negative 3. We had 1 at 1. And 1 at 5. So, and I'm not going to make this real specific. I'm not going to go like, oh, it has to be a certain direction. I just want to have an idea. What does it look like? So I know the roots. I know what where the graph starts, where it ends. Now I'm just going to play connect the dots. So when I go up to negative 3, it has a multiplicity of 1. So I'm going to go through like a line. I know that in order for me to get to my next root, I have to come down. And then I look at 1, and I see it has a multiplicity of 2. That means it's a bounce back. So I'm going to hit, and I'm going to bounce back. And then my x equals 5, no multiplicity, so that means a multiplicity of 1. So it looks like a line. And the graph looks like that. So if I wanted to be more specific, I can. If I wanted to find the Y-intercept, and you'll see here in the notes, it looks like they're finding the Y-intercept. Just take 0 and plug it into your function. Plug it into that function, that quartic. And when you solve it down, you get the Y-intercept. Now, there's no other name for a Y-intercept other than just Y-intercept. So that means this Y-intercept is the point 0, 30. But if you notice here, I got a few things going on here. We called these back in Unit 1 relative maxes because they're the top of a hill. We call this a relative min because it's the bottom of a valley. So what if I were to tell you that this point right here is negative 1.828, comma 128. This is the point obviously, you know that's 0, 1. I'm sorry, 1, 0. And this is the point 3.828. $128. Why don't you guys take a quick little step back here, and I want you guys to do something for me. I want you to tell me what the domain is, tell me what the range is, tell me when it's increasing. Yeah, let's do the mins first. Relative minimum. Why don't you tell me the relative maximum? Why don't you go ahead and tell me when is the graph constant? When is it increasing? And when is it decreasing? And why don't you tell me even, odd, or neither? What kind of function is it? Why don't you guys go ahead and do that real quickly here? All right, go ahead and pause the video and see if you guys can do that real quick. By the way, if you forgot what even, odd, or neither is, let me write that up here for you. I'm not going to go through and test the algebra on it, because being that it's a polynomial, we can tell right from the get-go. And we tested a lot of these guys first chapter. While I'm doing this, you can finish up here. F of negative x equals negative f of x. All right, the domain. Arrow to arrow, that means it is all real numbers. You could write it that way, or you could write it from negative infinity. Remember, infinities are always parentheses, to positive infinity. Either or, you take your pick. Range. Well, if you notice, these have, I didn't draw out the scale per se, but you notice these have a top point. There is a point that it goes to. If these were different, I would have taken the largest y value, but they happen to be the same. So I can just take both of them. My range goes from this arrow, negative infinity, up to 128. And that's going to be a bracket. My infinity is a parenthesis, that's a bracket. Relative minimums. Where's the bottom of the hill at? Well, I have one of those, friends. That's 1, 0. I have one relative min. My relative maxes, notice, I got a couple of them. And you can have more than one, so don't worry about it. It's totally okay to have more than one. Negative 1.828. Comma 128. And we have another one. So I'm going to make a little and symbol here. And 3.828. And 128. Constants. There are no flat lines, so I'm going to put D and E. Again, remember, if you just say x equals the x value of your relative extrema, the x value of your relative min, or your x value of your relative max, I'm okay with that. But there is no length to that point, so I'm okay if you just put D and E. Increasing. So remember, we said we're going to go left to right, pretend like we're walking. So it looks like I'm going up, therefore I'm increasing. Then I'm going down, so I'm decreasing. I'm going up, so I am increasing. And then I go down again, so I am decreasing. And these are short for increasing and decreasing domains. So that means this is negative infinity to the x value of that relative max. Decreasing. from negative 1.828 all the way down to 1. Again, these are all parentheses. And then I have another one. I'm increasing from 1 to 3.828. And if we do this right, between constant increasing and decreasing, we should use up our entire domain. Realize we only use the y values just when we write our relative extrema as a point, and for the range. Everything else is always x values. It's all domains. And if I were to plug this in here, I could figure out if it's even, odd, or neither. I'm not going to go through and do that because just lack of time, and I don't want to make this video too long. This one's actually going to be neither. When you plug in your even and odd and you check it, this would be neither. Well, friends, for you guys' fun and enjoyment, I think I'd like you guys just to make a rough sketch. You don't have to go through all this folderol. I just want you to make a rough sketch of what this looks like. So 3x times x plus 2. Just make a rough sketch of what this function would look like here. I want to know the zeros and factor in their multiplicity. And I also want to know the end behavior. Use the end behavior in zeros to make a rough sketch of what this particular function might look like. While you're doing that, I'm going to erase the board here. Magic Eraser likes to have fun. You guys are probably like, William's quiet, I'm trying to do it. Or some of you are like, Williams, hurry up and get done so we can see the answer. Boy. All right, I'm going to go ahead and start the answer. So if you need more time, pause the video. All right, let me see if I can do this real quick. Need a little XY graph going on here. And since I'm just making a rough sketch, all I really need is my X's. You're like, Williams, they're in Texas. Yeah, not quite. All right. So I'm going to go ahead and take a quick gander at what my roots are. I see an X here, therefore that's going to be a root. So 3x. The only reason this is a root this time, it wasn't last time. The only reason it's a root this time is because there's an X there. So that means X equals 0. And what exponent does it have? 1. We'll come back to that in a second. So if it's 1, no multiplicity to worry about. Our next one we have x plus 2. All right, so we're going to go and make that one x plus 2. So that's the factor, and we're going to use it to find the root or the 0, which is -2. What exponent does it have? Well, it's a 1 as well, so therefore it has a multiplicity of 1. Therefore, really no multiplicity at all. But don't worry about it. All right, x minus 4 equals 0. There's my next one. So if that's the factor, that means the 0 is 4. The root is 4. And I look at my exponent, it's 3. So that means it has a multiplicity. So it's a multiplicity of 3. So we're going to put on our, go ahead and draw these up here. So I had one at 0. I had one at -2. And I had one at, oh, where's that at? 4. Okay, so these are my zeros. Now I'm going to do my end behavior here. So my end behavior, I look at my exponents, 1, 1, and 3. So the degree then is 1 plus 1 plus 3. My degree is 5. So no matter where I end up, I'm going to be starting in the opposite spot. So if that's my degree, I need my leading coefficient, because I need to know if it's a positive number. My leading coefficient is a +3, so it is a positive number. So that tells me then that I'm going to finish, if it's positive, I'm going to finish going up. And the degree then, since it's an odd number, it's going to be doing the opposite. So it's going to finish down. And then we go through the lines. Here we go. -2 was a single, so I'm going through like a line. Got to turn to get to my next one. 0 didn't have multiplicity, so go through like a line. And then the last one had a multiplicity of 3, so I got a point of inflection. So up, flat, up. There we go. There's the sketch. All right, let's keep going on our fun and exciting way here. We've got some more of the, oh, there's our answers right there. You got some more you could do from general form and whatnot. We're going to skip that intermediate value theorem because we want to do something else with it differently. All right, so we're going to solve these. This should have the word solve out here. I'm not really sure what happened to it. I went on a coffee break or something. Can't blame it. All right. So we're going to solve these, friends. So to begin with, I have -4x². So to state the domain, the range, the zeros, y-intercepts, increasing, decreasing, relative. We're not going to do that. All we're really going to do here is we're just going to solve it. We're not going to graph the function. We're not going to do all that. We just want to go ahead and solve these. Yeah. We've already gone through and reviewed how to do all that. You can do it on your calculator if you want to. What I want to know about is what are the zeros? What are their zeros and what are the multiplicity? So if I'm looking for a 0, that means that's when f of x equals 0. So if I want to find this first one, it means I want to take this function right here, and all that we're going to be dealing with today is just the zeros. We're not going to do the rest of it right now. I mean, we just did an example of that. We don't need to overkill it. So we're going to go 0 equals -x⁴ plus 4x². And this is why we did our factoring at the beginning of the year. So first thing we always do on factoring is, do we have a greatest common factor? And you guys would say, yes, we do. Now that first one had a negative in front of us, so I'm going to pull out a negative x². And that leaves me with x² and then -4. So 0 equals -x² and x² -4. Then we're going to take a little look-see at it and go, all right, well, what else can we do? Whatever is left inside my parentheses, that's what I'm going to be messing with. So inside my parentheses, I have x² -4. If there's 3 terms, I'll do my box and diamond, but 2 terms means I'm going to look for one of my special things. Is there difference of squares, sums of cubes, or difference of cubes? And in this case, we have difference of squares. They're both perfect squares, so I'm going to write it twice. Our first square root of x squared is x. Square root of 4 is 2. And then we make 1 plus and 1 minus. And notice, I'm going to have 3 roots here. So if x squared equals 0, I didn't need to put that square there. I just did it anyways. X equals 0. And that means that it has a multiplicity of well, because I have that exponent. See that exponent? That means that I have a multiplicity. So x equals 0, multiplicity of 2. I take my next factor, x plus 2, and that means the root is -2. No, its exponent was 1, so that means no multiplicity. X minus 2 equals 0. So x equals 2, or a multiplicity of 1. Well, friends, I'm going to give you guys a couple to try just because, well, these are a lot of fun. How about, I'm going to go ahead and just set them equal to 0. So we're finding the zeros of a couple functions. Why don't you guys tell me, yeah, I should probably write it first like this. Tell me the zeros of 2x cubed minus 5x squared minus 3x. Go ahead and tell me the zeros for that. And why don't you guys also tell me the zeros for, let's try f of x equals, let's go x cubed, that could be fun, plus, oh, let's try 4x squared minus 9x minus 36. All right, friends, go ahead and solve it. I'm just going to set these equal to 0 real quick, and then I'm going to let you pause it. All right, pause the video if you want to have a little more time. All right, so here we go. I'm going to give it a shot here. I see 3 terms. That nothing wrong with that. Is there a number that will divide out of that? Maybe a variable. In this case, I just see a variable. I believe that x can come out of it. We left with 2x squared minus 5x minus 3. So we get 0 equals x times 2x squared minus, that was a square, not a cube. I'm telling you, I struggle making 2's with my mouse. Minus 5x minus 3. Okay, so how many terms do I have? Turns out I have 3 terms left. So that tells me I'm going to be using a box and a diamond. I can do that. We're going to ignore that x out front while we deal with the rest of this here. All right, so 2x squared minus 3 minus 5x. 2x squared times negative 3 is a negative 6x squared. That looks like a negative 6x to me and a positive 1x. So minus 3 x 2x, and looks like a positive 1 here. So I still have that x out front. I now have an x minus 3 and a 2x plus 1. And friends, if you notice, I don't have any exponents other than 1. So these are all going to be a multiplicity of 1. So we can just go ahead and solve them as is. So x equals 0. X minus 3 equals 0. So I take it from a factor and I turn it into a root. Which means I take it from being equal to 0 and I get it by itself. 2x plus 1. I'm going to take it from a factor. So factors we set equal to 0. Keep saying that over and over again because it's going to come into play here in a second. And we set it, we go ahead and solve it. X equals negative 1/2. All right. Some of you maybe saw this last one and thought, what the heck? 4 terms? Now let's find out. Yeah. Looks like I got 4 terms here, and it doesn't look like anything divides out of anything. That's okay, because friends, I noticed something about my generic rectangle. It has 4 spots. Well, that's awfully handy, because if I have 4 terms, and I have 4 spots in my box, chances are, but I can pop them right on in there. We always say the first term goes first. We've said the last term always goes bottom left. Notice, I got 2 middle terms. I have 2 empty boxes. It doesn't matter where I put it. I can put it anywhere I want to. So I can put 4x squared here. I can put it in the other spot. It doesn't matter. All that matters is that the 2 middle terms just go in one of these, each of these spots. I like it when I got 4 terms. It takes out the diamond part of it. So I have, let's see here, an x squared there. I have a minus 9 there. X and a positive 4x. I love it when I have 4 terms. A lot of times you guys will go, oh no, not 4 terms. 4 terms is great. Although it does not help when I put a x after that 4. So I have a factor here, x plus 4. X squared minus 9, well, I need to go a little further with that, it looks like, because still got a square in it. Still got a square, so I'm looking at it real quick. Since it has a square, I think, all right, well, there's 2 terms. Square, I need to check it real quick to see, is it a difference of squares, sum of cubes, or difference of cubes? Well, again, I notice, friends, that I have 2 perfect squares. So I'm going to write them twice. So square root of x squared is x. Square root of 9 is 3. And I make 1 plus. And I make 1 minus. And friends, if you notice, all 3 factors are different, so there is no multiplicity here. So we're going to set each factor equal to 0 and turn them into a root or a 0. Kind of makes sense that we say they're equal to, that they're zeros, because a factor is equal to 0. Equals 0. So x equals -3. And x minus 3 equals 0. And I know, friends, this is our long video. This would be like 2 or 3 days in Algebra 2 or Integrated 3. So I'm just going to apologize now. We're covering a lot of stuff here. But they flow pretty nicely. All right. What if I give you something where I ask you to tell me, where I give you the actual zeros, and I ask you to tell me what the polynomial is? Now, first of all, you need to know something about a polynomial. Polynomials will not have radicals in their, as one of their terms. So if I have a root that's a 2 plus 7, we're going to have something called its conjugate. So if 2 plus root 7 is a root, turns out we have a theorem that says 2 minus root 7 also would be 1. Kind of cool. What if -1 plus root 3 was a root? Why don't you pause the video real quick and see if you can figure out what else would have to be a root then? Did you get it? All right, so it would be -1 minus root 3. You just switched the middle term. And the reason for that is when we multiply out, it will make the radical go away because there are no radicals in a polynomial. So if x equals 2 plus 7 is a root, then my theorem says that x equals 2 minus root 7 is a root. So we have all our roots. What we need to do is we need to turn them into factors. And like we said everywhere, to find a root, you take a factor and set it equal to 0. Well, if I want to take a root and turn it back into a factor, that means I have to set it equal to 0. By the way, x is always positive on these. So even though it'd be easier to subtract the x to the side of 2 plus root 7, turns out we got to move those guys over. X has to stay positive. So x minus 2. I don't know why I put a 2 under there. That's goofy. Plus root 7. All right, so what we're going to do here, friends, is we are going to take these and we are going to start multiplying. So if we're going to write them out as a list of factors. So a list of all the factors multiplied together. So our polynomial would be all these factors multiplied together. And what we're going to do here, friends, is we are going to go ahead and pair up these, and we're going to start multiplying them out here. We're going to multiply those two. Let's multiply these two. We're going to multiply. We're going to multiply what those would look like. So this is a 1 by 2. So I'm going to multiply these two together here. I have an x and an x plus 5. Because our job now is to go ahead and multiply all these things out. So x plus 5. Whenever you're multiplying together and you have radicals, always do those radicals together. That way you can get those radicals to drop out. They always go together. So what do we got there? I got an x. I got a minus 2. I got a minus root 7. I got an x minus 2 positive root 7. All right, so we're going to multiply here a little bit. This one right here will be x squared plus 5x. So all these things would have normally been covered in integrated 3, but with you guys being out on COVID, you guys missed some of this. So that'd be a minus 2x. Again, it's nothing really all that bad. It's just a little bit time consuming. Root 7 times a negative root 7. Well, when you square a radical, the radical goes away. And I'm going to do these in another color because I want you to see something. X times root 7, well, that would be a negative x root 7. Positive x times positive root 7, notice. These ones are opposite each other. That's why we multiply the radical by the conjugates, because it makes the other one go away. And it allows us to have something that's a little bit easier. Negative 2 times negative root 7, well, that's a positive 2 root 7. Likewise, negative 2 times positive root 7, that is a negative 2 root 7. Again, notice all the root 7s have something they cancel out with, which is fabulous, because when we're multiplying, when we get our polynomial, a polynomial will never have any radicals in it. So this first answer, I had x squared plus 5x. And this next one had x squared minus 4x. 4 minus 7, that'd be a minus 3. And friends, we just got to multiply one more time together. I know I can hear you right now. I'm tired of multiplying. Oh, it's all right. It's not that bad. It's a little tedious, but there's worse things in the world. X squared plus 5x. Then we have x squared. That's a weird looking x squared, isn't it? Minus 4x minus 3. All right, go ahead and multiply these out. So x squared, that's x to the 4th minus 4x cubed minus 3x squared plus 5x cubed minus 20x squared minus 15x. So we were able to take it and multiply it all the way out to come up with our problem. F of x equals x to the 4th minus 4x plus 1x cubed minus 23x squared minus 15x. Well, friends, I hate to do it to you. I know this video is going to be kind of long, but I got to have you guys try one as well. What if I give you these two roots right here? There is one that has x equals negative root 3 and x equals, let's try 1 plus root 2. Why don't you pause the video and see if you can come up with a polynomial, a function of least degree that has integral coefficients with these roots. Why don't you go for it? All right, here we go. Sure, you guys pause the video. So I have x equals negative root 3. And I have x equals 1 plus root 2. So remembering what we know about radical roots, I know that means that x equals a positive root 3 as well. And I know that means that I also have x equals 1 minus root 2. Because if it's a radical, that means the conjugate also is a root. So my roots, x plus root 3 equals 0. So we're turning them into factors real quick. X minus root 3 equals 0. X minus 1 minus root 2 equals 0. And x minus 1 plus root 2 equals 0. So we're going to write it as a list of factors, as a product of factors, some people call this. All righty. This will probably be our longest video of the entire year, guys. So you guys are being troopers. I appreciate it. All right, we're going to multiply these two together right here. And I'm going to multiply these three together. Or those two together, sorry. So you guys are checking your work as we go through here. It's a little bit tedious. All right, so our first one, we had x squared minus 3, and I'm going to do the other two in a different color again, just so we can see what happens. Minus x, or plus x root 3. Again, anything that has a radical, if we do it right, will go away. Minus x root 3. X squared minus x plus 1 minus 2. And then everything that has a radical better go away. So minus x root 2 better have something that it partners up with, plus x root 2. And what is this? Positive root 2. And a negative root 2. So when we combine our like terms here, friends, we get f of x equals x squared minus 3. Notice radicals are gone. And x squared minus 2x minus 1. So we have x squared minus 3, x squared minus 2x minus 1. And we are going to end up with a fantastic polynomial. Shoo. You guys are being troopers, I tell you what. So f of x equals x to the 4th minus 2x cubed minus 4x squared plus 6x plus 3. I can make that just a little bit easier to read, I think. There we go. All right. One final thing, friends. No word problem. Everybody loves a good word problem. So take a second, see what you can do with it. So go ahead and pause the video, and then we'll walk our way through it. All right, here we go. It's time to walk. I know this whole thing is 24, but if you notice, I've cut off an x, I've cut off an x, I've cut off an x, and I cut off an x. So that means this was 24, but I cut off 4 x's. Likewise, friends, the whole side on this side was 24, but notice I cut off an x and I cut off an x, so therefore I cut off 2 x's. And since that's the case, that means the height of our whole shape here is indeed x. Now I noticed something here. That's not the color I want. That's the color I want. I noticed something here. Kind of looks like I could pull a 4 out of that. Kind of looks like I could pull a 2 out of that. So if I pull a 4 out of here, friends, it kind of looks like I end up with 6 minus x. If I pull a 2 out of here, it looks like I have a 7 minus x. I lied. That's a 24. Looks like I have a 12 minus x. My 24 didn't really come out real well, did it? So 12 minus x. So if I'm coming up with volume, volume is length times width times height. So volume, in this case, it's going to be in terms of x, is going to be length times width times height. So our length, well, that was the 4 times the 6 minus x, so I'm going to put that in there. All righty. And then the width, well, that'd be the 2 times 12 minus x. And my height, that would be x. So if I were to go through and multiply all my terms on the outside, I had a 4, I had a 2, and I had an x. If I were to multiply those together, friends, I believe I'd end up with 8x. So that's where the 8x came from. And then if you notice, I still have my 6 minus x there. So sometimes it's fun to use polynomials just to kind of model different situations. The second part said determine the domain of the function. Well, math students you guys know that if I set each of these factors now equal to 0, I go ahead and I end up with these zeros of our function. So we're going to make just a rough sketch of what this looks like and see if we can't use that to help us figure out what the domain would be. So let's go ahead and take a second there, just like we did at the beginning of today. Go ahead and make a rough sketch of what you think that graph would look like. Rough sketch it. Think about where the zeros would be. They all have a multiplicity of 1. Okay. So we make a rough sketch now. Here we go. My degree. The degree is 3, so that means I'm going to start the opposite where I finish. My leading coefficient is a positive 8, so that means I'm going to end high. And if I'm going to end high, that means that I had to start low. So notice, if I'm below the x-axis, that means I'm in negative volume, right? So we know that's not really the case. So here we go. I have a volume, but I'm negative volume again. Well, that can't be the case. And therefore, that can't be the case. Well, the only values I'm left with are between 0 and 6. If I use anything greater than 6, that's a negative value. So the green would be a negative value if I use anything greater than 6. Anything less than 0, that's a negative value. So anything greater than 12, that's also a negative value. So my domain then is going to be anything between 0 and 6. Sketch the graph of the function and find the value of x for which v of x is a maximum. All right, so we know our maximum is going to be somewhere out here. So just a real quick brief. I know we already saw the video on how to use our graphing calculators, but just a real quick brief view of that again. So you're going to type in, hit the y equals button. And under y sub 1, go ahead and type in that function there. And then you're going to type the word graph, all right? You notice when you hit the graph button, it's not going to come out the way you want it to. So you got a couple things you can do. All right, if you don't like the way it looks, that's okay. Option number 1, you can make your graph, you can fit it. So if you hit the button zoom, this is what a lot of people like to do. I don't really like to do this way. And if you scroll down until you get to number 0, so that's the 10th thing down there, you'll see a thing that says zoom fit. You could do this if you wanted to. Again, I don't like it, but you could. The other thing you could do if you wanted to, and this is where I usually like to go, because I like to kind of control and mess around with it a little bit. You could go here to where it says window. Now for your window, it's going to say a few things here. Let's see if I can't type it out real quick. X min, X max, X scale, Y min, Y max. We don't need to go past that. Y scale, all that stuff. Don't worry about it. So what it's going to say is going to say this X min, it's going to have it at -10. +10. The X scale, you don't need to worry about. We'll always just leave that alone. That's at 1. It's always going to go from -10 to +10. It always goes back and defaults to that. What I recommend doing is I like to play with it a little bit. So I know that I'm only dealing with values between 0 and 6. I know my X-intercepts are anywhere from 0, 0 to 12, 0. So for me, I'd probably change that to -1. I'd probably change that to 13, since make sure I can see all my values. I don't deal with negative volume, so I guess I could have left that at -10. And then I would have played around with my positive volume till I could found something that I kind of like. In this case, I'd probably use +700. And then once I've done all that, then I would have hit my graph button after that. And what it does is it just frames up your graph a little bit better. So now we worked on this already to figure out how to come up with your relative max. You had this back on the day of our first test, but just in case you've forgotten, you go to second. So that's that blue button, second. And it's going to say trace. And when you do that second trace, you're going to get to this word above it, CALC, which we really like. That's the word calculate, friends. Calculate. All righty. And just for the fun of it, when you calculate it, there's going to be a screen that comes up. Number 1 is going to say value. We don't need that one. Number 2 says 0. So if you wanted to find the X-intercepts, so you could find the zeros. Again, we're not doing that one. We practiced that one on Thursday afternoon. Number 3 is the word minimum. We don't want that one. The one we want today is 4, because we are trying to find the maximum value. So our calculator wants to do it for us. Maximum. So this is the one that we are going to go ahead and hit. We want this one. Maximum. All righty. When you do that now, I'm going to ask you a series of questions. So the first one is going to ask you is left bound. And then it's going to say right bound. And then it's going to say guess. All right, left bound, right bound, and then it's going to say guess. Well, the left bound, like we did on the calculator video, you can use your arrows. But if you notice, I know that my left bound, I can't go past this X-intercept, right? So if I know I can't go past that X-intercept, I could actually just type that number in and make that my left bound. So I'm going to do that. I'm just going to say 0 and then press enter. And then my right bound, well, I know I can't go past this right intercept because that's where my domain is. So I'm just going to make that my right bound. So 6. Guess, don't ever guess, just press enter. And then what's going to happen is it's going to go ahead and pop up here, and it's going to tell you now what that volume is, right? What that volume is. So in this case, it's going to come back and say, it's going to tell you that your volume is 2.539 and 665. 0.1075. So for us, then the X value that will give us the maximum volume is 2.539 inches. And the maximum volume then would be that Y value of 665.1075 inches cubed. All right, and last thing, friends, last thing. Once you've messed around and you've screwed around your window and either you zoom fit it or you change the window, as soon as you're ready to go, put it back to what it's supposed to be. As soon as you're ready to go, put it back to what it's supposed to be. Go to numbers, hit your zoom button, go scroll down to number 6, where it says Z standard. Press enter on that, and it will undo everything you did and put your calculator back the way you want it to be. Guys, you did a lot here. Totally dig it. Probably the most we've ever have to do for the entire semester. We had a lot to cover. Again, a lot of this was stuff we would have done last year, but because of COVID, we had to go back and cover it. Not a big deal. All right. So practice up, and I'll see you guys in the morning.